So what happened in this lab is that an object with minimal drag, but with some drag, was dropped on the ground, and the object was measured through free fall, and its velocity and position was measured using the tracker application. The goal was to measure the position and velocity of an object in free fall, and it was to compare it with two computational models, which one had no drag and one had drag prevalent. Now the key equations, here you can find it here. Here's change in momentum, velocity update, position update. Gravity is negative mg in the y direction, and drag was defined as the drag coefficient b times the magnitude of velocity squared, aka the speed squared. Now here's the tracker video. Right here we got the tracker video. The axis is linked by my max crest right here, and that's where the origin, and that's where it's dropped from roughly. And this blue line is the meter stick being calibrated to meter length. That way we know how far the object was dropped, and we have accurate units. So here, right here, is the drop of the paper right here, and as you can see, each spot was marked, and that is how we got the data without drag. Here's the mass of the paper, roughly 0.00362 kilograms. Here's the initial position. What the heck is your dictionary? I hate you. The initial position, which is a little bit more than 0 because the axis wasn't exactly the top of the screen. It was near the top, but not quite there. So it actually started above the paper started above the x-axis. It started falling after 3.5 seconds passed. So that was why t equals 3.5. Now here is the gravitational constant, 9.8 meters per second squared. Here's the force. Here is the velocity update equation using the Newton's momentum principle. Here's the position update equation. And then that's it for model 1 without drag. Now here's the model with drag. Now everything's the same. Let me quickly fix this. This should be 4.04 seconds. Of course, I just changed it to do some experimentation. But 4.4 seconds. Everything is the same except this drag coefficient is not 0. It is 0.001 to show that there is in fact drag in this model. Here in the bottom and top left is the tracker data, so the actual data. Here in the top right is the glow script model 1 model without drag, and bottom right is the model with drag. Now as you can see over here, for some reason the velocity is a lot lower than it should be according to computational model, and the paper was a lot lower at all instances of time compared to computational model. And as you can see here, drag does not really make the situation more accurate, or the model more accurate to this real life scenario, because there was this error in the data that caused the velocity to be a lot lower than it should have been. Now, those are the graphs. Here are some results error. As you can see, there's a pretty big disparity between both computational models and the observed data. The drag did not really help make the model any more realistic to what actually happened, which is filled with error. The initial heights were matched to the computational model, so the initial conditions were matched, but that did not matter because they deviated from each other. So one error in the tracker model was that the paper was spinning in the air, so I didn't actually track the same part of the paper every time. That could cause some error. Additionally, there could have been some accidental throwing of paper, because sometimes when you need to drop something, you accidentally add some force to it. What does it all mean? So terminal velocity. I think I already talked about this. When the drag force cancels out the gravity force, and that's when the magnitude of the velocity is so high that the drag gets really high. And at that point, the net force should be 0, and the object should continue to fall at a constant velocity. Now, that never happened in the computational model or in the video because we were not given enough time, but as you can see in the graph on the bottom left, it starts to level out, and eventually, given enough time, the drag will be canceled out by the force of gravity, which will reach terminal velocity. If the object was initially thrown downward, you would think it would have a greater downward force, thus it should take longer to reach terminal velocity. However, if you look on the bottom right, this is the graph that was thrown with the 0, that was not thrown, it was just dropped. And the graph on the bottom left is the one that was the graph of the object that when it was dropped. And as you can see, it levels out a lot later when there's initial velocity, so it actually takes longer for you to reach terminal velocity if you throw an object downwards. And that is the end. Thank you for watching. Bye-bye.